Imagine this. You're falling into a black hole. Time slows down. Space warps around you. And at the center, poof, everything crushes into a single point of infinite density where the laws of physics just break. That's the nightmare we've all been told about black holes for decades. But what if I told you that this singularity, the heart of darkness in every black hole, might not even exist? What if it's all been a mathematical mirage? Buckle up, because today we're diving into a game-changing idea from one of the legends of astrophysics that's flipping our understanding of the universe upside down. This isn't sci-fi. It's cutting-edge science from 2023 that's still sending shockwaves through the physics world. If you're ready to question everything you thought you knew about black holes, hit that like button, subscribe if you haven't, and let's jump in. Okay, first things first. Let's make sure we're all on the same page about what a black hole even is. Picture a star that's run out of fuel. For massive ones, gravity wins the battle against all other forces, and the star collapses inward. It shrinks smaller and smaller until its mass is squeezed into a region so dense that not even light can escape. That's the event horizon, the point of no return. Anything that crosses it is gone forever from our universe. But what happens inside? According to Einstein's general relativity, the theory that rules gravity on cosmic scales, all that matter keeps collapsing until it hits a singularity. A singularity is this bizarre point where density becomes infinite, space-time curvature goes to infinity, and our equations just spit out nonsense. It's like dividing by zero in math class, the universe's way of saying, "Error, physics not found." This idea has been around since the 1930s, thanks to folks like J. Robert Oppenheimer. Yeah, the atomic bomb guy, who first crunched the numbers on stellar collapse. But it really took off in the 1960s and 70s with the singularity theorems from Roger Penrose and Stephen Hawking. These guys proved mathematically that under certain conditions, like in a collapsing star, gravity inevitably leads to a singularity. Penrose got a Nobel Prize for it in 2020. Their work assumed things like smooth spacetime and paths that light rays, called null geodesics, follow straight to that infinite crunch. It was elegant, it was terrifying, and it became the cornerstone of black hole theory. Hawking even built his famous radiation idea on it, where black holes slowly evaporate over time, leading to paradoxes like, where does all the information go? But here's where it gets juicy. Black holes aren't just theoretical anymore. We've got pictures. In 2019, the Event Horizon Telescope snapped the first image of a black hole's shadow in the galaxy M87. And then, Sagittarius A star at our Milky Way's center. These beasts are real, and most of them spin fast. That spin matters because the math for rotating black holes is different. Enter Roy Kerr, a New Zealand mathematician who, back in 1963, solved Einstein's equations for spinning black holes. His Kerr metric describes how space-time twists around a rotating mass, creating effects like frame dragging, where space itself gets pulled along like a cosmic whirlpool. Kerr's work explained quasars, those super bright objects powered by black holes, and it's been the gold standard ever since. Fast forward to 2023. Kerr, now in his 90s and still sharp as a tack, drops a bombshell preprint on Archive called "Do Black Holes Have Singularities?" Spoiler, his answer, maybe not. Kerr isn't saying black holes don't exist or anything crazy like that. He's poking holes in the proofs that guarantee singularities. See, the Penrose-Hawking theorems rely on those null geodesics, the paths light would take, always terminating at a singularity. But Kerr shows that in his own metric for rotating black holes, that's not true. He found examples of light rays that zip through the interior without ever hitting a singularity. Instead, they spiral around forever, getting arbitrarily close to the event horizon, but never quite ending in infinity. Let me break this down with an analogy. Imagine you're at a classic fairground, a festival, and there's this thrilling stunt show called the Wall of Death, also known as the Motordrome or Well of Death. It's a huge wooden cylinder, like a giant barrel standing upright, about 10 to 15 meters tall and wide. A daring motorcyclist, or sometimes even a car driver, rides into the bottom of this cylinder. They rev the engine, speed up in circles at the base, and then, amazingly, they climb up the walls. Thanks to centrifugal force pushing them outward against the wall, they start looping horizontally, higher and higher, eventually riding completely parallel to the ground, even upside down near the top, defying gravity like it's nothing. Now, imagine the singularity as the bottom of a funnel. Everything slides down to that pinpoint. But in Kerr's view, for real spinning black holes formed from actual stars, not idealized math, the funnel might not have a bottom at all. Those geodesics don't crash. They loop or extend indefinitely. Kerr argues that the theorems assume too much smoothness and ignore the messy reality of how black holes form. Stars aren't perfect spheres. They have lumps, magnetic fields, and all sorts of chaos during collapse. Plus, most black holes rotate, and in the Kerr metric, the singularity isn't a point, it's a ring. But even that ring might be avoidable if the paths don't force you there. This isn't just nitpicking math. If singularities don't exist, it solves a ton of headaches in physics. First off, singularities are where general relativity breaks down. We need quantum gravity, a theory that marries Einstein with quantum mechanics, to fix that. Ideas like string theory or loop quantum gravity try to resolve singularities by turning them into something fuzzy, like a ball of strings or a quantum foam. Kerr's work suggests we might not need that for black holes. Maybe the classical theory holds up better than we thought. It also ties into the black hole information paradox. Hawking radiation says black holes evaporate, but if there's a singularity, information gets destroyed, violating quantum rules. No singularity? Maybe information is preserved in some exotic interior structure. And get this, if black holes don't have singularities, what about the Big Bang? The universe's origin is often described as a singularity too. Hawking and Penrose extended their theorems there. So Kerr's critique could ripple out to cosmology, hinting that the Big Bang wasn't an infinite point, but something else. Maybe a bounce from a previous universe. Mind-blowing, right? Now, let's talk evidence. Kerr's paper is theoretical, not observational, but it's sparking debates. On physics forums and Reddit, experts are buzzing. Some say it's a valid point. The theorems have loopholes. But others argue it doesn't disprove singularities entirely. It just shows the proofs are incomplete. Real black holes might still have them, hidden behind quantum effects. Future telescopes like the Next-Gen Event Horizon could probe closer, looking for signs of weird interiors. Gravitational waves from merging black holes, detected by LIGO, might also give clues about what's inside. But why does this matter to you and me? Black holes aren't just space monsters. They're keys to understanding the universe's extremes. They power galaxies, shape cosmic evolution, and test our theories to the limit. If Kerr's right, it means we're closer to a unified physics without those pesky infinities. It reminds us science isn't settled. Even icons like Hawking get challenged. That's the beauty of it. Question everything, test ideas, and let the math lead. All right, wrapping this up. We've covered the basics of black holes, the traditional singularity scare, Kerr's revolutionary twist, and what it could mean for the future. If this blew your mind like it did mine, drop a comment below. Do you think singularities are real, or is Kerr onto something? Share this video with your space nerd friends, and if you want more deep dives into astrophysics mysteries, hit subscribe and turn on notifications. I've linked Kerr's paper in the description for the brave souls who want the full math. Thanks for watching. Keep looking up, and I'll see you in the next one.